In this lesson, we'll review quadratic function. A quadratic function is any function that can be written in a form of quadratic trinomial ax squared plus bx plus c, where a, b, c are real numbers with the leading coefficient different than 0. A graph of a function like this is called parabola. What are the properties of quadratic function? Well, first of all, we recall that any quadratic function results in a parabola. The domain of such parabola is all real numbers, since this is a polynomial, so any real number can be taken for x, and we are able to evaluate this expression. How the coefficient a influence the graph? Well, if a is positive, for example, here we have two functions with a equals 1, just a basic x squared, the blue one, and the red one, 2x squared. If you observe the value at 1 is approximately here, and 1 squared is also 1, so 1 results in a value 1, and that's the point that belongs to the graph. Now, if you want to graph g of x, which is 2x squared, this value 1 becomes 2 because it's multiplied by 2. So it is stretched vertically twice. So we end up with the red graph. And we can observe that if we multiply this 1 by a positive coefficient a, 1 or 2 or 3 or even 1/2, our graph will still rise from 0 to this particular positive number at 1. So the arms will be always positioned up. Therefore, if a is bigger than 0, the graph opens up. And if a is smaller than 0, for example, like this gray graph, negative 1/2 x squared, then the graph will open down. You can observe this on the value at 1. Since 0, 0 is the vertex, the value at 1 will determine the direction if the graph opens up or if it opens down. In this particular case, if x is 1, the value is negative 1/2, approximately here, therefore the graph opens down. So if a is negative, the graph opens down. So as we see on this diagram, a is really responsible for how narrow or how wide is our function, and also if the function has arms up or down. The other property of parabola is its symmetry. Any parabolic shape is symmetrical along the line passing through the vertex. The same on this diagram. Here's the vertex, that's the line passing through the vertex, this is the axis of symmetry. So any parabola is symmetric with respect to a vertical line passing through the vertex. Very important property of a quadratic function is the relation of the coordinates of the vertex with the formula. For example, we can rewrite the general form of a parabola as above in a standard form that actually tells us what are the coordinates of the vertex. H and k in this formula stands for the coordinates of the vertex. So the formula goes a, which is the coefficient that is responsible for the shape of the function, then is x minus h squared plus k, where h and k are the coordinates of the vertex. H in terms of a, b, and c can be written as negative b over 2a. That formula really comes from the procedure of completing the square of the general form of quadratic function. And also the k coordinate, the second coordinate of the vertex, can be found by just evaluating our function at the first coordinate. But if we do that, it turns out that this formula becomes the negative discriminant, negative delta, where delta is b squared minus 4ac, over 4a. So either we can remember the first and the second coordinate of the vertex in this form, or we can remember the first coordinate and find out the second coordinate by evaluating function at the first coordinate. This is very useful form for graphing parabolas, since as soon as we know the vertex hk and we know the leading coefficient a, then we can already graph the shape. So let's state that the vertex has coordinates negative b over 2a and negative delta over 4a, where delta is our discriminant b squared minus 4ac. As we mentioned before, since parabola is symmetric with respect to the vertical line coming through the vertex, then the equation of this axis of symmetry, since this is a vertical line, has a form x equals to the first coordinate of the vertex, which is h. We can derive even more properties of quadratic function if we check just the leading coefficient a. As soon as the leading coefficient a is positive, then we have a situation like this, which means that the parabola has its minimum at the vertex. Therefore, the range of such function starts from the vertex and goes up. So we know that the second coordinate of the vertex, which is k, is the minimum, and also that the range of such parabola starts from k and goes up, so from k to infinity. We also know that the function f is decreasing from minus infinity up to the first coordinate of the vertex, that means up to the h, and then it's increasing starting from the first coordinate of the vertex towards infinity. So decreasing here and increasing over there. If the leading coefficient is negative though, then we have this kind of situation where the value k of the vertex is the maximum value. Therefore, the range starts from minus infinity and go up to k. And then the function f increases to the left of the vertex and decreases to the right of the vertex. Since we're talking about x coordinates, then the interval on which the function increases is from minus infinity till the first coordinate of the vertex, which is h, and decreases from h to infinity. Okay, so if we know so much about standard form, we can take advantage of it and graph the following functions without referring to any table of values. So we don't need any calculations, we just need to list the coordinates of the vertex, which are the numbers that you see in a bracket with opposite signs, so just one, outside with the same sign, so it's 3. And also take care of the leading coefficient -2. That gives you the idea how steep is the function around, just one step from the vertex. So we can plot the vertex at 1, 3 over here, and then go by the steepness, which is -2. That means that our shape should be positioned downwards, and if we go one step across, the value will drop 2 steps. So this point and also to the other side 2 steps. Now with parabola, if you go 2 steps across, then when you square it, 2 squared is 4. However, we multiply this by -2, so it will be -8 steps. 2, 4, 6, 8. Oh, the point will be here and symmetrically to the other side. That's how easy you can graph your parabola. Somehow like this. In the second example, what are the coordinates of the vertex here? We don't have any number under the square close to x, so this first coordinate is 0. It's like x minus 0. And then second coordinate -1. So 0, -1, that's the vertex. And the steepness is 1/2. That means we can go 1 across and only 1/2 up, both ways, to the right and to the left. Normally, if we go 2 steps across from the vertex, the value should go up by 4, but we multiply this by the coefficient 1/2, so it will go up just by 2. So as you see, this parabola will be wider. And we try to volunteer the shape of the parabola, somehow like this. Obviously, we could check more points, but these 5 points are usually enough to see the shape. In this exercise, we have two functions given in a general form. In order to bring them to the standard form, we need to go through completing the square procedure. So let's convert this to the standard form, and then it will be easy to graph. So how do we use completing the square? Well, we use the first two terms. We want to complete the square for these first two terms. So we use the x, the same sign, and half of the middle coefficient 4, which is 2. Square it and then subtract perfect square of the number that we took in the bracket, which is 4. So whatever we have here, it really means the same much as the first two terms. You can easily check by squaring it that this procedure really works. Okay, then add 1 and combine your three terms. So overall f of x equals x plus 2 square minus 3. So now we can read the vertex. Coordinates of the vertex are opposite to the number that you see inside the bracket, and the same sign of the number outside of the bracket. And now we're ready to graph. So -2, -3 is over here. And since the leading coefficient is 1, we really have the shape of standard parabola. So 1 across 1 up, 2 across 4 up. Those are the points to connect. I can use different color. The shape looks somehow like this. Oh, it looks like I forgot to put some marks on each axis on these diagrams. So always remember to put at least one number on each axis to indicate the scale on each number line. Okay, the last question. Here, in order to complete the square, I would advise to get rid of this minus, for example, by dividing by -1 to the other side, and then we'll have negative f of x equals x squared plus 3x minus 1. We can complete the square in this form and then solve back for f of x. So negative f of x equals bracket x plus half of this coefficient, which is 3/2, square it, subtract perfect square of the number in the bracket, so 9/4, copy the rest. Now what we need to do is to combine these two numbers and also change the sign because we really want f of x by itself. So it will be negative bracket x plus 3/2 square. Now this 1 is the same as 4/4, so 4 and 9 is 13, and we're switching the sign, so it's plus 13/4. Okay, so let's list the coordinates of the vertex. It is negative 3/2 and positive 13/4. Well, this time maybe it's not so easy to graph, but we can still approximate this number. So negative 3/2 is like -1.5 somewhere there. And 13/4 is the same as 3 1/4. So 3 1/4 approximately here. So the vertex will be approximately here. Okay, the leading coefficient is -1. So we know that the graph will go downwards, and the shape of it is just about the same as standard shape of parabola. So 1 across 1 down, and 2 across 4 down. 1, 2, 3, 4, approximately here. Similarly to the other side. And then let's graph the shape. Approximately like this. So let's put the scale. This is 1 and this is, let's say somewhere here it's 3. So the vertex is tiny bit above the 3. In the next example, we're going to find the range of this particular quadratic function and state the maximum of the function. Since this function is a parabola with arms going down, it looks somehow like this, then we really need to look for the vertex, and then the range would be from -infinity up to this y coordinate of the vertex. We can use two different ways to find the vertex, either by completing the square, and changing this formula to the standard form of parabola, or by using direct formula for the vertex. Well, maybe in this exercise we can still practice more of completing the square procedure. So I would divide by -1 to bring the negative to the other side, and start with the leading coefficient 1. That will be plus 8x and minus 3. Then to complete the square, we are preparing a bracket. We're taking x and the same sign. We're taking half of the middle coefficient, which is 4, square it and subtract perfect square of the number that we took in the bracket. So it's minus 16, and then copy the rest, -3. Therefore, if we solve this equation for f of x, which means multiply by negative again, so f of x would be equal negative x plus 4 square, and since that was -19 and we need to switch the sign, it becomes positive 19 here. Therefore, the coordinates of the vertex are -4, opposite to whatever we see in the bracket, and 19, the same sign from outside of the bracket. Okay, so we already have the maximum value. The maximum value is actually 19, the second coordinate of the vertex. So we can record maximum value equals 19, and we can easily state the range of this function as -infinity up to 19 inclusive. In the next example, we need to find the minimum value of this particular quadratic equation and determine the values of x such that f of x equals 2. Since the leading coefficient is positive, then the parabola has arms up, and we indeed have the minimum. So we're looking for this minimum value, which is second coordinate of the vertex. Just for change, this time we can calculate the vertex directly from the formula of the vertex. So the second coordinate of the vertex is k, which is equal negative delta over 4a, where delta is b squared minus 4ac. So let's calculate. Our a, b, and c are the coefficients 2, 1, and -2. So negative b squared, which is 1, minus 4a, which is 2, c, which is -2. Everything over 4a. So it's 4 times 2. And when we simplify this, inside the bracket we can see that it's 1 plus 16, so it's 17. With a minus, it will be -17 over 8. So this is the second coordinate of the vertex, -17 over 8. And that's our minimum. So we can give the final answer. The minimum value equals -17 over 8. Now the question also asks for finding the values x such that f of x is equal to 2. What does this mean? It means that if I replace f of x by 2, I need to solve this equation. So let's bring everything to one side. It will be 2x squared plus x minus 4 equals 0. And what we are looking for is the roots of such equation. The roots can be calculated by using quadratic formula, which is -b, -1, plus or minus square root of b squared, which is 1, minus 4, times a, which is 2, times c, which is -4. Everything over 2a, which is 4 as well. So this simplifies to -1 plus or minus square root, and under the root we have 1 plus 32, so it's 33. Everything over 4. Okay, so those are the x values that will satisfy the equation f of x equals 2. The properties of quadratic function, the maximum or minimum, is quite often used in optimization problems, problems like the following one. A farmer uses 1200 feet of fence to enclose a rectangular region and to subdivide the region into 3 smaller rectangular regions, like on the diagram, by placing fences parallel to one of the sides. Find the dimensions that produce the greatest area. Okay, so we need to investigate area. Let's try to write the area function. Area of a rectangle is just length, which is marked by L on the diagram, times width, which is marked by W. So L times W. Unfortunately, this function contains 2 variables, and we really need to find the function with 1 variable, otherwise we won't be able to minimize it. So what we really need to do is to come up with the relation between L and W, some other equation that will relate L and W, and then solve this equation for one of the variables and plug it in to the area formula in order to bring everything to 1 variable. This other piece of information is exactly here. A farmer uses 1200 feet of fence. So this is the total length of fence that we can use. The overall length consists of 2 lengths, 2L, and 4 W's, 4 width, plus 4W equals 1200 feet. That's our relation between L and W. Okay, what we can do here? I would suggest that we'll divide this equation by 2 to low down the coefficients, so we end up with L plus 2W equals 600. From here, it's very easy to solve for L. This is 600 minus 2W. And that will be our substitution expression that we are going to use in the area formula over here. So instead of L, we can write 600 minus 2W and then times W. So this time we have already area as a function of 1 variable, and this function is a parabola, is quadratic, because W times W is W squared. However, this quadratic has leading coefficient negative, so the resulting parabola will actually look somehow like this. And this is in fact a desired form of parabola. We don't need to multiply through because the factored form is usually easier to use. How? We can figure out what are the roots of this parabola. So one root comes from just W, so the W could be 0, or the other root comes from this bracket. Well, this bracket is 0 and W is 300. That's easy to solve. So W is 0 or 300. What does this really mean? That means that our function a of W could be seen in a system of coordinates as parabola that comes through 0 and 300 on the w-axis, and that's the area function. So that would mean that the midpoint between 0 and 300, because of symmetry of parabola, the midpoint is the point when we can expect to get the greatest area. So this midpoint is easy to calculate. It's an average of 0 and 300, which is 150. This is the W that produces the maximum area. Okay, so we can give the final answer, the W with the subindex maximum. W that produces the maximum area is 150. Therefore, the length that produces the maximum area is, and we need to follow the formula for the length, which is here, is 600 minus 2 times 150, which gives me 300. Therefore, we can state that the dimensions producing the greatest area are 150 by 300 feet. And one more application of quadratic function. A charter bus company has determined that the cost in dollars of providing X people with a tour is given by this linear function C. A full tour consists of 60 people. The ticket price per person is $15 plus 25 cents for each unsold ticket. Determine the revenue function. Okay, let's consider revenue function. Revenue in respect to the number of people that go for the trip. So that was X people going for a trip. What is a revenue function? Well, it's the cost per person times number of people. So cost per person times number of people X. Okay, so what's left to do is to find out what's cost per one person. How a person is charged. It is $15 plus 25 cents for each unsold ticket. Well, let's start building the expression. $15 for sure, and then 25 cents, 0.25, times the number of unsold tickets. Okay, but how many tickets is unsold? If X people is going for a trip and there was 60 seats in a bus, then X could be smaller than 60, and the remaining part, 60 minus X, that gives us the unsold seats. 60 minus X. This is the unsold number of seats. So this whole expression represents just a cost per one person. Now we still need to multiply times the number of people going for a trip. Well, let's simplify this function. That will be 15 plus 0.25 times 60 is another 15 minus 0.25x, and then everything times x. Since 15 plus 15 is 30, so we have 30x minus 0.25x squared. Next, we need to find the profit function. So if we have a revenue, profit in respect to the number of people going for the trip is the revenue minus cost. So the revenue is that much, 30x minus 0.25x squared, and then we subtract cost, which was given in a problem. So minus bracket 180 plus 2.5x, and then after simplifying we end up with negative 0.25x squared, and then linear term 30 minus 2.5 is 27.5x, and finally minus 180. So that's our profit function. Now, to find the company's maximum profit, we need to maximize this function, which is an upside-down parabola like this. So we really need to find out the second coordinate of the vertex, or generally find out the maximum point of the function. We can do it directly from the formula of the vertex, which is negative b over 2a and negative delta over 4a. So the second coordinate will be the maximum value, and the first coordinate will tell us at which point, that means for how many people, this maximum value will be achieved. However, in this particular example, I would like to introduce the calculator again and see how can you use graphing calculator to find out the maximum directly from the graph. Okay, first let's plug it in the function to the calculator, which is negative 0.25x squared plus 27.5x minus 180. And the first step would be to try to graph it just directly in Zoom 6 window. Well, it looks like it produces only part of the graph, so we need to modify window. How can we do that? If we look at the function, for x equals 0, we have negative 180. Since this is quadratic, it grows pretty quickly up. Let's change the window in such a way that we'll see x maximum till 100 and y minimum maybe 100 as well, negative 100. However, the y maximum, let's try 500. See what will happen now. Oh, we see a little bit more, but we still don't see the tip of the graph. So we need to change the window again, and maybe let's try 700. That's pretty nice. We already have this tip, and that's what our interest is, the maximum of the graph. So now we can use the calc function, second calc, and we are going to calculate maximum, so push number 4. Now the calculator asks about left bound, that means before the maximum, and our flashing point is exactly before, so that's okay. If it's not close enough, we can always scroll by using arrows. For example, closer. Enter it. Then the calculator asks for the right bound, so scroll till you go after the maximum and enter again. So this tells the calculator where to look for the maximum point. Okay, now your guess, you can scroll a little bit closer to the maximum that you think it is and enter again. So we see the maximum point has coordinates 55 and 576.25. The 55 really represents the x coordinate, which is the number of people that produce the maximum profit, and 576.25 cents is the maximum profit. So we've got the maximum profit to be $576.25. And this maximum profit happens when we sell exactly 55 tickets. So the number of people that maximize the profit is 55. And on the diagram, it looked somehow like this. The maximum happened at the x equals 55, and it's equal to $576.25, which is over here. And the last optimization problem is about Norman window. A Norman window has the shape of a rectangle surmounted by a semicircle. The exterior perimeter of the window is 48 feet. Find the height h and the radius r that will allow the maximum amount of light to enter the window. So the height of the window that the question talks about is actually just this part, not the whole window, but just the height of the rectangle. And the radius is over here, r. In order to maximize the amount of light, we really need to maximize the area of this window. So let's figure out the formula for area. Area is composed of area of a rectangle and area of the semicircle. So the area of the rectangle would be the base, which is actually 2 times r, 2r, times the height h, 2rh, plus half of the semicircle, so half of the area of the circle, which is pi r squared. Again, the area function presented this way is a function of 2 variables. We really need a function of 1 variable, so we need one more equation that will relate r and h, from which we'll be able to solve for one of the variable, whichever is easier, plug it into the area function, and then investigate the new area as a function of 1 variable. So what is the relation between r and h? Here we have given perimeter of 48 feet. So what's perimeter of this whole window? We'll have to go twice along the h, which is 2h, plus the base, which is twice the r, plus half of semicircle. So it's 1/2 of 2 pi r. However, the 1/2 and 2 cancel, so it's just pi r. That will be the whole perimeter. We are talking about perimeter outside of the window. That means just this part. And we are not adding this middle bar here, just the outside. And this perimeter equals 48. From that formula, we need to solve for one of the variables. It's probably easier to solve for h. Let's solve it for h. So that will be 48 minus 2r and minus pi r, and then divided by 2. This could be simplified a bit. It could be written as 24 minus r and minus pi half r. So that's our substitution expression. We're placing it instead of h in the area formula. So the area will be already a function of r, and it will look as follows. 2r and then 24 minus r minus pi half r instead of h, plus pi half r square. When we multiply through the bracket, it becomes 48 r minus 2r square minus pi r square and plus pi half r square. These two terms are like and they are easy to add. So this could be written as 48r minus 2r square minus pi half r square. Pi half minus pi is minus pi half. Finally, it's a good idea to factor the r, so it will be easier to see the roots of this function. That's after factoring. And then we can list the roots. The first root is really easy, comes from this factor, so first root is 0. Or the second root comes from this bracket, so maybe we need to calculate on the side how much is the second root. It won't be very pretty, but we can still calculate. So 48 minus 2r minus pi half r equals 0. When? Let's bring these two terms to the other side and also factor the r. So we will have 48 equals r, and then it's 2 plus pi half. It's a good idea to put this under common denominator. Okay, so it's 48 equals r, and this is 4 plus pi over 2 as a coefficient. So r by itself is equal 48 times 2, which is 96, divided by 4 plus pi. Okay, so the other root is 96 over 4 plus pi. Great, we have the two roots. So if I draw the system of coordinates and try to place my parabola a of r, so this is a of r, and that's r, the roots will be 0 and 96 over 4 plus pi. And the parabola a of x goes somehow like this. So we can claim that the midpoint, which is exactly 48 over 4 plus pi, produces the maximum area for the window. That will be the maximum area, A maximum. And this is R maximum. Since the question asks us to find not only radius but also height, we need to use this formula to find out the corresponding h that produces the maximum area. That will be 24 minus r, but r was this much, 48 over 4 plus pi, minus pi half times r, which is again 48 over 4 plus pi. Well, as you see, this expression looks a little bit big and awkward, but we can manage. What can we do to simplify it? We could reduce the 2, making 24. We could put together everything under common denominator. So the common denominator will be 4 plus pi. Since this was just 24, it will be 24 times 4 plus pi. Here we didn't change denominator, still 48. And over there we didn't change denominator, is 24 pi. So after opening the bracket, the first number is 4 times 24 is 96, and then we subtract 48, so we end up with 48 again. And 24 pi will be actually cancelled with negative 24 pi, so that's very nice. Our expression becomes a lot simpler. It's just 48 over 4 plus pi. That's your H maximum. Surprise, surprise, we have exactly the same value as the R maximum. So we can give the final answer. The R maximum is 48 over 4 plus pi, and this is also equal to H maximum. Well, what does it mean for a window? How the window looks like? If this is my H, then the R is of the same length, and another R to the other side. So the window looks somehow like this. And then we have the semicircle here. So this shape of the window will allow for the maximum light.